Okay, this is my first attempt to present a lecture on symmetry method. It is symmetry method 2, lecture 9. We will try to solve some nonlinear PDEs in this lecture. In fact, this lecture is a mapping between one system and the other one. We will solve the difficult system with the help of easy system using symmetries of the systems. So let's start. These are the outlines of my talk. Differential equations and most probably partial system of partial differential equations. So equating the order epsilon terms of equation 37 and 38 we obtain. So what is the main techniques? We equate equation 3.7 and 3.8. So explicitly they implies this 3.9 and 3.10. So this is the mapping we need to map the given system on the target system. We will see it is hard to understand here, but we will see that it is not so hard when we take examples on this stuff on this concept. So in more compact form, these two equations can be written in this like these equations you see in 3.1. This is the more compact form of the 3.9 and 3.10, where XL is the nth order prolongation in the space x and u coordinate, and Z is the extended generator given in equation 3.4 in the ZW. So let's see 3.4. This Z is defined in 3.4. It is the generator in the target space 3.4. Yes, over here. This is Z. So this is the mapping between the given space and the target space. And the whole game is behind the symmetry generator. These are the symmetry generator in the given space, and Z is the symmetry generator in the target space. So all we need the symmetries admitted by the given system of differential equation, which will be 0, 1. And this Z is the symmetry generator of the target space. So we find the symmetries and put over here, we will get a system of partial differential equations. We will solve that partial differential equations, and we will get the mapping between the coordinates of the given system and the target system. Invertible mapping, there are theorems on invertible mapping. So we have two theorems on invertible mapping. The first one is this: when there is only one dependent variable, then we have a mapping given in equation 3.12. Z is a function of x, u, and u1. W is a function of x, u, and u1. And w1, which is derivative of w with respect to z, is psi1, which is a function of x, u, and u1. This theorem is due to Buckland. Note that phi and psi are independent of u1. So there is a mistake in this lecture, in this equation. There is no u1. This u1 is not here. Z is a function of x and u. W is a function of x and u only. There is no u1. This u1 is extra, so this is a mistake. Only w1 depend on u1. Theorem 2. When we have more dependent variable, not one dependent variable, in that case our mapping will become this one. Z is a phi of xu and w is a psi of xu. This is a mapping only in the coordinate, not in the derivative. So the difference between the two theorem is here the derivative is involved. First derivative is involved, but in the second case, the first derivative is not involved. The mu is defined like this one. We need the mapping in the derivative, and we doesn't need the derivative. We only need mapping between the spaces. This theorem is due to Moeller and Maschet. Now, there are two types of mapping. One is the non-invertible mapping, and the second is invertible mapping. So where is the mu non-invertible and where it is invertible? This is a question. The non-invertible mapping occur where the number of symmetries of the given system is not equal to the number of symmetries of the target system. And mu will be invertible if the symmetries of the given system and the target system are the same. So we give example for each one. Here is construction of non-invertible mapping. And for this purpose, we have heat equation and Burger equation. Heat equation is a linear equation, but Burger equation is, I think it is non-linear. Yes, it is non-linear. So we will find this mapping, the mapping given in 3.14. This is a Hopf-Kohl transformation, and we are interested to find it explicitly by ourselves how this transformation defined. So we take heat equations, which is given in 3.15, and Burger equation, which are given in 3.16, and find the Lie symmetries of this equation and the Burger equation. So let's see their symmetries. These are symmetries of the heat equations. 3.17. This system contains all the symmetry generator emitted by the heat equations. These are 6 in number, while the Burger equation admit 5, 5 Lie symmetries. But what is common in them? You see, x1 is like z1, x2 is like z2, x3 is like z3 in the independent variable. You see the action of the independent variable is here, action of the independent variable is here, so this is the same action of independent variable action here and here are the same. The difference is only in the dependent variable. So the group action of both the sets are the same in the independent space, but they are different in the dependent space because this symmetry is in the dependent space, but I have no symmetries in the dependent space here. This part is in the dependent, but you see this is different from this one. So that means the group action in the independent space are the same for both the equation, whether it is heat equation or Burger equations. But the group action in the dependent space is different for both. And we will take that as a basis for our mapping. We put x6, we not put equal to 0 because it's not 0, but we assume it that s6, there is no x6, so that we left with the 5 Lie symmetries here and here, and there can be defined a mapping between them. Okay, so now we take a z6 which correspond to s x6, but we are not taking x6 as given in equation 3.117. This one we are taking it, we assume that it is 0, so that the mapping can be defined here. Now we have these commutation relation. You all know what is commutators, and this is the commutator. This is in the given space and this is in the target space. The why we are say that the the structure constant are the same for both the given space and the target space, because the action of the group in the independent space are the same. So that is an observation. Also we can calculate these structure constant. If they are the same, then we can proceed. So on the basis of the structure constant, we have the same structure constant, then we can proceed toward the mapping. We can define a mapping. There exists a mapping between the two spaces. The common group action on the independent variable space and the fact that the transformation must be non-invertible indicate that the simplest mu transformation mu, which map 3.14 to 3.15 mean the heat equation on the Burger equation. So we see from the observation that the group action among the independent coordinate are the same. So we leave that as it is. Z1 goes to x1 and Z2 goes to x2. And why we are taking this? This is clear from here that this is the symmetry generator is the same as this one. This is the same as this one. The first two parts are the same as the first two parts, which is the action of the independent variable. Similarly, this first two parts is the same of these first two parts. And this symmetry part is exactly the same. So the group action in this independent space is the same. That is why we are taking these like z1 is equal to x1 and z2 goes to x2. But the goal is to find this thing. And for this, we will use the mapping. Okay. It is seen in the previous slides that for the mapping we need prolongation. Let's see it again. You see this is a prolongation. So we need the prolongation on the one side and no prolongation on the other side. So we prolong these generators. So we need prolongation over here. And I think first prolongation. So that is why we find the first prolongation of all the generators in the given space. And we leave the second. And where this system come from the mapping given here it is. Yes, here. This come from here. We use this equation 3.11 or 3.9 and 3.10. This equation for the given heat and Burger equations give me this system. Now my goal is to solve this system. My goal is to solve this system. This is a system of, let's see, 2, 3, 4, 5. These are 5 equations, 5 PDEs, and we have to solve these PDEs for what? For this thing. We need this equation. So if we define this equation, then we know the mapping between the old and the new space, mean the given and the target space. So let's start solving this system. What these two equations tell us? These two equations tell us that psi is independent of x1 and x2. It only depends on u and its derivatives. So putting that information in the given system, the system reduced to this one. And this last equation tell me that psi is only depend on u1, not on u2. Now putting this information above in these three equations, we can get this solution. Students are advised to do a little bit effort here. Put this function only a function of u and u1. So this term is 0. This term is 0. This term is 0. So you left with two term here, two term here, and two term here. And from that you can easily find that psi is in fact this function. So now we succeed in finding a mapping between the target and the given system. This is the mapping which is called the Hope-Cole transformation. So why we find it? We find it for some purpose. And what is the purpose? The purpose is to solve the Burger equation, because the Burger equation is nonlinear. And we can solve the heat equation. Heat equation is linear and it is easy to solve. So finding you, put over here the derivative of u with respect to x1 and u here, I will get w. But what is w? In fact, w is the solution of the Burger equation. So solution of the heat equation give me solution of the Burger equation. So the whole game is that we solve a non-linear PDE with the help of linear PDE. And how it happened because of the mapping between the spaces. And how the mapping is defined, uh, the mapping is defined because of the symmetries of the given differential equation and the target differential equation. So the whole goal is to solve the Burger equation. Here is invertible transformation. Zalmi's find this transformation. For what? We have cylindrical KdV equation and KdV equation. So this is KdV equation and this is a cylindrical KdV equation. So I think this one, there is a one extra term over here. This is non-homogeneous. So we will take a mapping between the cylindrical KdV equation and the KdV equation, and we will find a mapping, and that mapping will ultimately give us solution to the KdV equation. This one. So let's start. I will go through this because this calculation and the previous calculation are the same. These are the symmetries, four symmetries of the cylindrical KdV equation. These are four symmetry generator of the KdV equations. So the number of symmetries of the cylindrical KdV equation and the KdV equation are equal. So there is a mapping you see in this equation. 3.31. We are interested in this sort of transformation. So let's see. Okay, the mapping between the symmetries and the symmetries give me this system. In fact, three our procedure is in 3.11. So that give me this system. This is system of PDEs. We will solve this system of PDEs, and the solution of this system give us the required mu, the transformation, which relate the spaces, the new and the old spaces. So uh, one of them is soluble. Either the given space is soluble or the target space is soluble. So one is soluble, the other is difficult to solve. So with the help of the solution given and the mapping given, we will find the solution. So the whole game is to solve this system. So I'm not going in the detail. You have to solve that. All sort of something is discussed over here. Your efforts are required in this case. So I'm going toward the solution of this system. See, this is the solution of the system. This is the solution of the system. And in fact, I'm interested in W because I can find you. I will find you. I will find you. Put over here. I'll find solution of the order equations. So I think you all have to go through these slides and learn what we did here in simple words. What we learn here, contact me.